Let us explore the X-ray diffraction and X-ray photoelectron spectroscopy analysis to confirm the structural compositional details of nickel tungstate nanosphere anchored polyaniline nanocomposite. It was prepared by using a hydrothermal route followed by a chemical oxidative polymerization route and explored as an electrolyte material for the determination of theobromine.
Determining theobromine in this experiment is important because theobromine is a naturally occurring compound found in cocoa and chocolate products that has both beneficial and potentially harmful effects. While it offers health benefits such as regulating immune function and supporting cardiovascular health, excessive or uncontrolled levels can pose risks, especially in sensitive populations and animals. For example, theobromine can cause toxicity in pets like dogs and horses and may have adverse effect on livestock when present in animal feed. Monitoring trace levels of theobromine in food ensures consumer safety, helps maintain food quality, and complies with regulatory limits designed to prevent toxicity. What are the materials used in this experiment? First, nickel tungstate. It is an inorganic compound known for its good electrochemical performance. It is used here in nanosphere form to provide a high surface area for charge storage. Next, polyaniline, a conductive polymer with an excellent electrical properties. It acts as a conductive matrix that enhances electron transport. Next, activating carbon, used as the negative electrode material in the asymmetric supercapacitor device. It is commonly used for its high surface area and conductivity.
There are 5 instrumentations that have been used in this experiment. First and foremost, the Bruker XRD Rigaku D/MaxB DMX 2200. It is used to analyze the phase configuration of the nickel tungstate polyaniline and combination of 2 nanocomposite. Second, Fourier transform infrared spectroscopy is used to evaluate the structure functionalities of the materials as prepared materials. Third, high-resolution transmission electron microscope. It is used to evaluate the microstructure and elemental content of the nickel tungstate polyaniline nanocomposite. Fourth, the micromeritics 2020. It is used to assess the specific surface area of the nanocomposite. Last but not least, X-ray photoelectron spectroscopy. It is used to analyze the chemical composition of the nickel tungstate polyaniline nanocomposite. The diagram shows a schematic representation of the synthesis of nickel tungstate polyaniline and nickel tungstate nanospheres anchored polyaniline composite. The product from the first step synthesis is a perfectly dried fine powder, and then from the second step of the synthesis it turns into a dark green colored precipitate. After addition of sulfuric acid and CTAB, now it is obtained as a nickel tungstate nanospheres anchored polyaniline composite.
Nickel presents a novel electrochemical sensor designed to detect trace amount of theobromine, a compound commonly found in foods like chocolate. This sensor uses nickel tungstate nanosphere combined with a conductive polymer called polyaniline to create a highly sensitive and selective detection platform. The main application of the sensor is in food safety and quality control, but it can rapidly and accurately measure very low levels of theobromine in complex food samples. This is important because monitoring theobromine helps ensure food products meet safety standards and protect consumer health. Compared to traditional method, this electrochemical sensor is faster, more cost-effective, and easier to use.
X-ray photoelectron spectroscopy has been chosen because of its surface sensitivity, chemical state information, quantitative analysis, and non-destructive. XPS is highly surface sensitive, making it ideal for analyzing the outermost layers of materials. It provides detailed information about the chemical environment of elements. XPS allows for quantitative analysis of elemental composition. It is generally considered as a non-destructive technique. XRD spectroscopy method has been chosen instead of other method because of its working principle. First and foremost, an X-ray beam is directed at the crystallometer. Next, the X-rays are scattered by the atoms in the crystal lattice. Next, the scattered X-rays interfere with each other and the resulting pattern is detected by a sensor. XRD spectroscopy can be classified as a qualitative analysis method because of the resulting diffraction pattern provides information about the material's crystal structure, different phase identification, and other structural properties.
Here are some advantages for using this method. First, high sensitivity and low detection limit. The combination of nickel tungstate oxide, ionosphere, and conductive polyaniline provides a large active surface area and efficient electron transfer, enabling detection of very low concentrations of theobromine. Next, good reproducibility. The sensor produces repeatable results across multiple uses and electrodes, indicating robust fabrication and reliable sensing. Next, compatibility with real food samples. The sensor has been successfully applied to detect theobromine in actual food samples, demonstrating its practical applicability. Last but not least, cost effectiveness and practicality. Electrochemical methods with such nanocomposite sensors are simpler, faster, and less expensive compared to traditional chromatographic or spectroscopic methods.
Let us analyze the spectral and microstructural characterization by using XRD and XPS. By referring to Figure 1 and Figure 2, Figure 3a confirms that expected elements present such as nickel, tungsten, oxygen, nitrogen, and carbon in the nanocomposite. The relative standard deviation is found to be less than 5%. Thus, nickel, tungstate, nanospheres anchored polyaniline nanocomposite can be a potential candidate for the determination of theobromine in real-time analysis. From the discussion, there is strong positive linear relationship between theobromine concentration and oxidation peak current. Second, there is strong positive linear relationship between anodic peak current and scan rate. Thus, it is proof that the electro-oxidation of theobromine at nanocomposite surface follows the adsorption control process. For the amperometric current time measurements, there is strong positive relationship between each addition of theobromine and oxidation current. Further, the sensing efficiency of nickel, tungstate, nanospheres anchored polyaniline composite modified electrodes has been proved by the detection of theobromine of food samples.
Is due to the synergistic effect between nickel tungstate and polyaniline, which provides a large surface area with more active sites and enhanced electrical conductivity. The sensor also shows strong operational stability and selectivity with minimal interference from other substances. Reproducibility tests using 5 different electrodes show only a 3.21% variation in current, with repeatability tests on a single electrode had a 4.12% variation, confirming consistent and reliable sensor performance. Overall, the nickel tungstate oxide electrode offers highly sensitive, stable, and reproducible detection of theobromine. Now, the limitation for using this method is high cost of materials and equipment, toxic organic solvents and chemical, and waste generation.
Throughout this article, it is alleged that novel electrochemical sensor capable of detecting theobromine in food with high sensitivity and selectivity has been developed using nickel tungstate nanospheres anchored on conductive polyaniline to form the basis of electrochemical sensor of detecting theobromine. It shows very good stability, reproducibility, and a low detection limit to allow the determination of theobromine at the trace level. Also in complex food matrices. Such method is a fast, cheap, and a realistic solution to conventional investigative and analytical approaches, promising future activities in food safety and quality control measures.